Welcome everyone, and thank you for joining our part two, Making Auto Negotiation and Link Trading Reliable and Why It Matters webinar, provided by UNH Interoperability Lab and Teledyne LaCroix. My name is Sherry Winslow, Marketing Administrator for Teledyne LaCroix's Protocol Solutions Group. For our presenters today, first we have Kay Doobie from the IOL team. Kay is the Operations Manager for the Ethernet and Storage Technologies and manages operations of Ethernet testing, as well as helps plan for future services. Kay also has the background as the Senior Copper ANEG Technician and Supervisor at the lab. From Teledyne LaCroix, we have Craig Foster, Product Line Manager for Storage and Networking. Craig has over 25 years of experience in system, application, network, and storage monitoring and load generation. Craig's primary focus is on storage performance and troubleshooting using wire level monitoring and generation solutions. Also from Teledyne LaCroix, we have Joshua Harsh. Josh is a field application engineer with over 20 years of experience in protocol analysis tools for Ethernet, Fiber Channel, SAS, SATA, and PCIe, and currently is the primary support engineer for Teledyne LaCroix's line of SAN analysis tools. For today's topics, we will answer the following. Does ANEG support parallel detection? What is the ANEG data rate? How to decode and interpret the different ANEG pages? How are LT messages sent when the link is not yet trained? What are presets and how do they work? Why is interop testing important for LT? We received some questions through the registrations as well, which we will cover. For any other questions you may have, please drop them in the questions box and we will do our best to answer them at the end. Also, to let you know, we will email all registrants the recording and the presentation slides within 1 week, and we'll include the part 1 on demand as well for those who missed it or would like to see it again. Okay, I will now pass this on to Kay to kick off our webinar.
Thanks, Sherry. So today I'm going to cover a couple of different questions that we received in our last webinar, as well as some that we received from the registration pages as we were prepping for this webinar. So we're going to start today with a parallel detection function. So the parallel detection function allows a device with auto negotiation enabled to establish a link with a device that has auto negotiation disabled. Now this does only work for a small subset of technologies. Most of these are legacy technologies and they are defined explicitly by the standard as being allowed to be used with this parallel detection function. It is not used as a substitute for, say, the downshifting technology, where two devices with auto negotiation enabled fail repeatedly to establish a link at their highest common denominator and therefore start decreasing their advertised abilities to try and link at a lower speed. Nor is it used as an alternative when two devices have auto negotiation either enabled or disabled but fail to establish a link, as you wouldn't expect a device to toggle its auto negotiation ability on or off just based on multiple failed link attempts. As mentioned, there are only a couple of supported technologies. So for our base T technologies, you have 10 base T and 100 base TX. Once you hit 1000 base T, you do need auto negotiation or an engineered link to establish that link. And then for our non-base T technologies, we have 1000 base KX, 10G base KX4, and 10G base CX4 that can be used with the parallel detection function to establish a link. So that begs the question, is parallel detection required or not? So the parallel detection function or the features related to it, yes, are required. This is listed out kind of easily seen in the PICS section of the IEEE standard. This is from the 802.3 version 2018. So the PICS just give kind of a summarized table of the requirements that are provided in that subclause. But furthermore, from the PIC RF5, which is not shown here, it is only required to actually be implemented and used if the device supports those technologies like the 1000 base KX, the 10G base KX4, or the 10G base CX4 that are allowed to be used in the parallel detection feature. So your device may never actually need to do this if your device doesn't support these technologies. So that's kind of just a quick rundown of the parallel detection function. Hopefully we were able to clear up some of the confusion that we had at the last webinar around how this technology is used and where it may be implemented. So from here, last time we did have quite a few questions on the data rate of ANEG and how would you establish a link if you're allowed to transmit at multiple different ANEG speeds or multiple different line rates with the ANEG abilities. So just going to try and clear up some of those questions. So just for convenience, I did take the summarized and slightly modified versions of the questions that we got on the previous webinar, as well as from the registration for this one. The big thing here is I just wanted to clarify that the data rate, or kind of that rate at which the DME pages and the pulses within those pages are sent, are explicitly defined by the standard. They have a very narrow window that they can be transmitted at. And this transmission rate is the same regardless of whether it's going to link up at 10G base KR or 10G base KX4 or any of the higher speeds. The auto negotiation sequence is sent at the same spacing regardless of the final link speed. So the picture was taken from the IEEE 802.3 standard from the 2018 version, and it just kind of shows a very, very small subset of that DME and how the clock pulses and where the data pulses show up. So your clock transitions kind of show that cadence of how frequently the clock and the timing is going to be sent. So this table is just also taken from the same portion of the standard, just kind of showing the transmission spacing and timing of all of those pieces. So as you can see, these are very, very narrow windows. The DME is going to be between 338.8 and 339.6 nanoseconds. There's only a small margin of 0.01% nanoseconds on how far from your typical 3.2 nanoseconds the clock pulses can be. Or sorry, that's the clock to data transition. But really this spacing is very well defined, and it does not change from device to device nor from technology to technology. When I was doing some research into kind of where the confusion was coming from, colleague Jeff Lepak, who's also our director, mentioned that it might actually be coming from the link training. And there is a section within the standard that I know Craig's covered some of, but looking at 72.6.10.2, where it actually defines how the training frames are built. The training frames themselves have a very fixed length, but within that training frame, different portions of the frame are sent at different rates. So for each of these portions, like that frame marker and that control channel, those individual pieces are sent at different data rates, but the frames themselves are always sent at the same rate between frames. So I'm hoping that this is where the confusion is coming from, and that the language here just makes it a little bit unclear as to what the data rate is in this kind of before we've brought up the link process. If this is not the section of the standard that is causing problems, please feel free to either put it into the chat or reach out to us at the end or afterwards, after the webinar is finished, kind of with the standard spec that's causing the confusion. Because this is the only one that kind of my team could come up with where it could be generating that confusion between where is the data rate, or what is the data rate of the ANEG process, and kind of that process before the link is established. So like I said, please let us know if you need more clarification on this, but the short answer here is that ANEG is always sent at the same data rate and at that same pulse frequency as defined by the standard. And it is the same regardless of what technology you are looking to establish the link at. And I think our final section for me for today is just mentioning that our IOL test plans do have several informative tests. I think most of our test plans in the Ethernet space do have several of these. So the big question here was, how are these informative only results helpful in solving some of the interop issues that you may see out in the field? So before we really dive into that answer, kind of did want to give a little bit of background on the purpose of our UNH IOL test plans. All of our test plans can be found on our website, which will be included in kind of the end cards of this webinar, as well as in the follow-up emails and the slides that you get from us. But the primary purpose of our test plans is to provide a consistent test procedure for the industry to test compliance to the standard. Our primary purpose is not necessarily to look at interoperability from a compliance standpoint. Obviously, we're hoping that as more and more devices are compliant to the standard, the interoperability will be better. But the test plans themselves are not necessarily defined exclusively for interoperability testing, with the exception, of course, of our interoperability test plan. These are designed so that testing may be done internally through the manufacturer as part of their engineering or their QA/QC process. It might be part of the integration process for a system integrator, to where they're testing the parts once they've integrated them into their product. Or it can be done by going to somebody like us or other places that can generate this third-party testing to either confirm your internal results or to generate reports that you're able to use for external marketing or sales purposes. So that brings us more to what's the origin of these informative tests. So they come from a couple different places. The IEEE standard does provide some guidelines for kind of optional behaviors. In earlier parts of the standard, they tended to use the word may to show where those places where the implementer has some flexibility in their product design. As the standard goes on, they start to be a little bit less clear on those optional guidelines, but they are built into the standard. There are also instances in the standard where there is no required behavior. I have an example of one of those coming up. So the informative tests really provide a procedure to test these optional behaviors or to test the gaps in between defined behaviors, so the engineers can understand how their devices will operate in these conditions. And then it is also used in some of our test plans for instances where, in order to run a test to check a certain behavior, we have to send it non-compliant something, whether it be transmissions, non-compliant signaling, non-compliant DME advertisements, just something that is non-compliant. There is no guarantees that all of the devices in a network are compliant. So this can help to see and ensure that your device is going to behave as you expect it, even when it receives something that it hopefully will never receive. So first example is one of those from that last bullet point. So we're looking at, from our test plan, a delimiter detect test. So this is part B. I didn't grab the whole test. But so the instructions are to send the DUT to MV pairs separated by less than page test min timer. That means that these MV pairs are too close together to be valid MV pairs. So the spacing is too short. So since this is an invalid spacing for the transmissions, sorry, it is non-compliant behavior that the device is receiving. So we're using the informative here just to let the vendor or the whoever is doing the testing know that this is how your device would behave in a situation where its link partner is non-compliant in this way. Now, the standard does provide that this is how it should behave in this environment. So that's where we're drawing the test from. But we do, again, want to ensure that your device is going to behave as expected, even if not all of its link partners are perfectly compliant. And then my second example is looking at one of those instances where there's a gap in the standard. So we're looking at our priority resolution function, and we're looking at part B, which looks at the non-Ethernet selector field resolution. So steps 1 through 4 would be sending DME advertisements with certain selector field advertisements and trying to see what the behavior is. Now for the Ethernet selector field, so that the one that is defined as Ethernet through the standard, that one obviously has a whole long line of things that we expect the device to do. That's kind of how we get to testing Ethernet. And there is also defined behavior for what happens if a device receives a reserved selector field combination. But the standard doesn't actually say what the device should do in the instance where it receives a defined selector field, but not the Ethernet defined selector field. So we have this test in here to, again, allow your device to know what it's going to do in the situation where it receives DMEs with a selector field that is defined, but not necessarily defined for the technology that you're looking for. So in this case, it might be, again, that your link partner is non-compliant and is advertising a different selector field. I think fire code is one of the other defined ones. And your device may or may not still enable its Ethernet PMDs. It may or may not still attempt to make a link, because the standard doesn't say that you can't, doesn't say that you should, but it doesn't say that you can't. So we leave this open to the implementer to try and determine, does it want to not enable those Ethernet PMDs because its link partner is not advertising that it's doing Ethernet? Or do we want to kind of allow the device to be a bit more tolerant of non-compliance and expect that if we're in an Ethernet network over some type of Ethernet cord with one device that supports Ethernet and the second device certainly looks like it supports Ethernet, which is why we plugged them in together, that even if it's not advertising Ethernet, we're still thinking that it is actually doing Ethernet. So it just gives a little bit of wiggle room to try and design your product, again, how you want to maximize its abilities in the networks of the world. So as far as kind of the interoperability piece of this goes, these results might come up perhaps if you've got, if we do have a device in your network that is advertising a non-Ethernet selector field, but everything else is fine. Like it complies to all other features of the Ethernet function, but for whatever reason, its selector field gets set wrong. And you have two devices where one is able to establish a link with it and another device isn't. It might be that one device is still enabling its Ethernet PMD, whereas the other one is not. But yeah, so I believe that covers my section here. If you do have any questions on specific informative tests, please feel free to let us know, but they are included to try and provide as much coverage as we can of the standard and to provide as much information to the engineers who are receiving our reports, both for those who are developing the actual PHYs as well as for those who are kind of integrating those PHYs into their final products. So from here, I believe I'm going to pass it off to Craig, and he can take it away.
In our previous presentation, we talked in brief about auto negotiation pages and how they are used to communicate what speed a device can support. And we talked a bit about how these pages are transmitted. Today, I'd like to talk more about what LT's auto negotiation pages have and more about the next pages that are part of this process. So there are multiple types of auto negotiation pages. The format and available fields for each one is different. First, there are what we call the base pages. These are the most common because anyone supporting auto negotiation has to support and send this page. Next is the message page. After this leads us to the extended technology abilities, which communicates additional speeds and capabilities that may not be covered in the base page. And finally, I want to talk about some of the approved updates to these pages and how they'll be used in the future. So let's start by talking about base pages. We've talked a bit about base pages in the past. Base pages are the first auto-negotiation pages sent, so they must be supported by any device that uses auto-negotiation. Other pages may not necessarily be used if their capabilities don't require them to be, but this one must be sent. It describes what speeds are supported by the device as well as what FEC capabilities it has. This is a sample image from our analyzer software that shows how this is structured. There are 1-bit fields for a number of speeds and capabilities, and you set the bit if that speed and capability are supported. Basically, the two devices exchange these pages and will negotiate to the highest speed they both claim to support. They will also say which types of FEC they support, such as RSFEC or base RFEC. Now, in addition to these fields, there are some additional fields that will help with the flow control of this page, as well as the next pages. First, let's look at the acknowledge bit. Both the devices connect together and will start sending these pages at the same time. Once a device sees and accepts the pages being sent to it, it will then set the acknowledge bit in its own auto-negotiation pages, so the other device will know its pages have been acknowledged. A device can't move on to the next page until the current page it is sending has been acknowledged. To aid in this, the page also has a transmitted nonce field and an echoed nonce field. The device sending the page will choose a nonce value for the transmitted nonce. And when it wants to set the acknowledge bit, it will also take the transmitted nonce value it has received and set it in the echoed nonce field of its own base page, so there's no confusion on which page is actually intended to be ACKed. Then there is the next page bit here. If this bit is not set, then there are no more pages and we're done with the auto-negotiation. But if it is set, then there are more auto-negotiation pages to send, and we can move on to sending those pages. Now, any of the pages sent after the base page are collectively called next pages. And there are different types of next pages. Typically, the first next page is going to be the message page. The message page is a formatted page that helps us to know what type of page is coming next. We know how the next page should be formatted. Here you'll see there is a message code that describes what page is coming next. Now, there are new speeds that do not currently have a bit to represent them in the base page. So if you want to negotiate to a speed like 400 gig base R8, you won't find that bit in the base page. So you'll need a next page to communicate this capability. In that case, when you get to the message page here, you want to set the message code to 5, which indicates the format to be used in the next page will have these abilities. And we'll take a look at that page in a bit. But for now, know that you'll want to set this to 5. You also see that there is a T bit or a toggle bit. This bit is flipped when you start sending a new page. If you have a lot of different pages to send, this is a helpful bit to watch to make it easier to know when you are looking at a new page. There's also this message page bit, which when asserted here tells the receiver that we are indeed looking at a message page so that we know how this page is supposed to be formatted. So after the message page, we move on to describe the extended technology abilities. With newer devices, some additional speeds and abilities have been added, and next pages have been updated to support these abilities. You'll see here additional speed capability bits like 50 gig base R2 and 400 gig base R8 that you won't see in the base page, so they're put here instead. In addition, you will see additional FEC capability bits. So this is where you can communicate your ability to support RSFEC, KRFEC, and low latency RSFEC. Here you'll also have the ability to request which of the given FEC types to use. So we've talked about what is currently supported in auto-negotiation, but now let's consider a bit about the future here. Because Ethernet's not going to stop at just 400 gig, there are at least 5 new speeds planned. In contrast, the base page has a few more bits in its format that we could use, but it only has 3 bits left over that we could use for speed capability bits. So where can we put capability bits for more speeds in auto negotiation pages? Also, in addition to the new speeds, we have additional FEC modes that we have to plan for, and the number of these FEC modes that will need to be supported has not yet been published. Well, in phase 1, we use one of the 3 bits we have left over in the base page to add another capability bit for 800 gig base R8. Now this alone will buy us quite a bit of time, but we still have all the other advanced speeds and FEC capability bits that we'll have to support in auto negotiation. So in phase 2, we use our last 2 available bits to add a bit for the extended technology ability fields and another one for the extended FEC capabilities. Now asserting these 2 bits means in the next message page, we're going to have speed capability bits that set if these additional speeds are supported. So in that message page, you can see we define some of the bits here a little differently. There'll be bits set aside for 1.6 terabytes, 800 gig CR4, 400 gig R2, and 200 gig R1. In addition, some of the bits will be set aside for extended FEC modes to determine if these FEC modes are supported and can be used in the given device. And with that, I'll turn the time over to Craig to tell us more about link training.
Thanks, Josh. So on the registration page, we had the option for users to submit questions that they'd like to see covered in this webinar. One of the questions was, can link partners exchange the presets and very low data rates reliably even before the link training starts with these values? And the short answer to that is no. And that's very similar to some of the questions that we had in the initial webinar, which led us to want to do another webinar to follow up in more detail on how all this works. Even though they can't be sent earlier and the link is going to be at full speed, they are being sent with Manchester encoding. So even though this frame is at 200 gig, they are being sent with Manchester encoding, and we'll look at what that means on the next page, which in a way kind of effectively reads to a lower data rate. They are also sent over and over again. If you look at this example right here, this is saying that there's 28,468 training sequence frames sent over and over. The systems do not have to achieve frame lock in order to communicate. In fact, that's one of the fields within the training sequence that we'll look at. And frames with Manchester's errors should be ignored. Manchester encoding basically sends every single bit over 8 times over with a 0-3 transition and a 3-0 transition surrounding it and in the middle. So basically, it could be looked at as being sent at a data rate of 1/4 of whatever the link speed is, because they're sent 4 times in a row. In addition, there's these flags from 3 to 0 or 0 to 3 in order to help figure out where the data is. So let's look at the link training frame. The top section of it is the control field, and this is where we're going to make our requests. And the bottom portion is a status field, and this is where we're going to reply to the requests that we're receiving. The first part of the request is the initial condition request, and we have the option to either specify that we'd like one of the presets to be used or that we want to make a change to an individual coefficient. When we're making the presets, generally they're sent to the coefficient 0, but all presets are changed. So they'll set to these values. The most common that we see in the traces that we have from our lab is preset 2. We also do see the default preset 1 being sent as well, and we'll look at some of those, the output from some of those later on. The next field is the modulation and precoding request. This specifies whether it's going to be PAM2 or PAM4 or PAM4 with precoding. There's some more information on these web pages about these different settings. And you can see the different eye diagram. PAM2 is kind of similar to NRZ. We just have the 2 values, and PAM4. So this is where you could see the value of going from 3 to 0 and 0 to 3, because in either case, it's going to appear the same. The next field is the coefficient select. So this is the the coefficient that I'm going to make a request to either increment or decrement or to hold. And you can see that there's also the possibility that I could use values that are not there. So there's some unknown values that could be used, as there's a big gap in the possible values. The next field in the control section is the coefficient request. So this is where I'm going to ask for the coefficients to be either held, in which case no change should be made, incremented, in which case the value should be incremented by somewhere in this range for these coefficients, and in a smaller range for the -2 coefficient. The same values are used for decrements as well. And then there's the option to say I'd like to go back to no equalization or preset 1. The next field is receiver ready, and this is basically indicating that we've completed the link training on this lane, and I'm ready to start communicating. Now let's take a look at status. In the status, we reply back with that we agree that we're either going to do PAM2, PAM4, or PAM4 with pre-coding. So it's a response to the request. The next field says, have we received frame lock yet? Have we identified frame boundaries to let the other side know how we're doing as far as bringing up our link? The next field is the initial condition status. So this replies to if they say they want to use one of the presets, have I actually made the update already or not? So once it's updated, then we can move on to the next request. Another field in the status is the parity field, and it is really just there in order to make sure that we have even parity. It doesn't really have any meaning other than that. It's just to ensure that there's even parity within the frame. The next field is a coefficient select echo, so that is to indicate that I'm going to reply to a request to a specific coefficient, and so there was a request made to that coefficient. I'm going to reply about that coefficient and whether or not I've made the change requested. There's several possible responses to that. Now, one is that I have not yet updated it. The hoped for one is that it has been updated. The other possibility is a coefficient is out of limit, so it could be that it's reached a minimum value if it's asking to be decremented, or a maximum value if the request was to increment. There's also coefficient not supported, so that would be in the case of one of those unknown coefficients being sent. Equalization limit indicates that while it would be possible to increment that value if other coefficients possibly were set differently, it's going to arrive at a value that exceeds the transmitter's voltage, so it will not be incremented. But there's a possibility to possibly arrive at that value if other coefficients are changed. The other is the coefficient is at the limit as well as the equalization at its limit, so there's no point in trying to adjust it to get to that value. Let's look at what this looks like over time. So this, you can see the gray is holds being sent. The purples are a request for a particular preset to be sent. The blues are requests for increments or decrements to be made. And then the lighter greens are responses that those changes have been made. Yellows are one of those indicators that a limit of some kind has been reached and the change will not be made. And then hopefully at the end, you get this green that everything's been completed and the lane is up. So one of the things that I wanted to know is, what does this look like over time? What values do these coefficients arrive at? So I've created a VSE script to go through traces and see what are the values that are being requested. And you can see for different lanes within this trace, there's lots of different values that are being requested. In this case, and in all cases, in all the traces that I have, there are no changes to the -2 coefficient. And so it seems pretty consistent that that one is left alone. These other ones often have different changes. You can also see what presets were sent and if any maximum or minimum conditions were reached, and did everything complete successfully. So there can be a variety of these results depending on the speed and number of lanes that are present. Again, you can see what presets are common. Preset 2 is being used in this case. Here's again another case with preset 2 and maxes being hit, which seems to be fairly frequent. We've seen here's a case where no presets were sent, and we went with preset 1, and actually it looks like there were no requests made because that is what preset 1 looks like. Here's a case where some of them did hit maximums and others did not. We had a variety of values that were present in for different lanes. And here's a case where preset 1 was specifically requested, and that was actually the resulting value. No increments or decrements were requested as well for this speed. Now, one of the things that I wanted to know is how consistently do we arrive at the same coefficients over and over again? So I went about having a link flap several times so that we could see, do we arrive at the same coefficient values consistently? Because in my mind, that would give me some assurance that the link is more likely to be reliable and stable, and that the link training process is reliable as well. So in this case, we had 17 link training phases for port 10 and only 15 for port 9. That's just an artifact of when we took the trace. But I can see in all cases, again, it used 0 for the CE-2 coefficient and 16 cases, so fairly consistent, but there are some different values for this. Now, one thing I will note, it does say here I have preset 3 being sent, but that is a bit of red herring because that frame and all the frames where preset 3 was seen did have Manchester errors. So it wasn't a real request, and it points out the importance of making sure that you ignore the values where you have Manchester errors. Otherwise, things would get very confusing. So that's all I had to cover, and with that, we'll go ahead and move on to questions. So we have a question that came in that says, do you have a scope that decodes CL73 DME pages? That's more, if you're asking about scopes, we're on the protocol analyzer side of the equation, and I don't know about our actual scopes, whether or not we have that. Josh, is that something you know?
No, I don't know any more about the scope side of business than you may. I mean, we can decode the training sequences and the auto negotiation pages themselves just within the protocol side, but I'm not sure what we have with scopes.
Yeah, so was that really specifically about scopes or about protocol analyzers, Patrick?
And then just to follow up from the IOL side, we're using custom tooling for this, so it's not something that's available off the shelf.
Yeah, so Patrick's question was protocol analyzers, and yes, we do offer that. The next question is, sometimes we can see in the trace a lot of loss of sync indications during the link training phase, even close to completing the link tracing. What would this indicate? Josh?
Yeah, a loss of sync, it means that, as seen from the analyzer anyway, that we lost sync, that the signal has basically disappeared, or is so bad that we can't make an interpretation of it at that point. We frequently would see something, a loss of sync, if right after the completion of the training, that if you see a loss of sync between that and the rest of your traffic, that part is normal, as is a loss of sync between the auto negotiation and the link training stages there. What you might also see is if training is having a problem to progress all the way to completion, you might see some loss of syncs along the way during that process, and that's just indicating that you're having a problem with the link training. There might be a problem with the cabling or something along the way, but you're not able to from a lower level perspective, from electrical perspective, we're just not getting a clear enough signal in order to actually complete the link training.
All right, the next question is, will this type of protocol analyzer also map out parallel detect mode if normal DME pages don't load? I'm not sure I understand the question completely. Josh, do you?
I'm not familiar with it either, with the parallel detect. If we're not doing any auto negotiation, then we just jump straight into the layer 1 traffic after that.
Right, but we would see the auto negotiation being sent by the one side. It's just that normal, I'm not sure what normal DME pages don't load means. So Michael, if you want to maybe elaborate, and we'll go ahead and go on to the next question. And it was about who we can contact about a demo and a quote. So that's always a good question. Patrick, we have your information and we'll follow up. For the one more question came in. It says, have you experienced more interop issues with CL73 or with CL72? I think that's a question for both Josh and Kay, since they have more experience in this.
Yeah, from our side, of course, being a neutral third party, I can't give too many details there, but it's kind of hard to really piece out when we're looking at a some type of interop link that's going to be coming up using DMEs. It's not always easy to tell whether the error is coming up with the clause 73, so that ANEG piece, or with the clause 72 link training piece. I'm not sure, honestly, that I've seen anything too consistent to where I'd be able to say that one is far more than the other. Even thinking to some of the plug fests that we do, kind of seeing both sides, to where we'll see issues with both the ANEG portion and with the link training portion. So I don't really know that I have kind of which one is the bigger problem versus the other.
Yeah, my response would be something similar along those lines. I don't know if I could really say that one is more common than the other. I mean, I guess they're dealing with the link training, since we are dealing now with the individual signaling levels. There's a lot that can go wrong with things that might be in the way, cable lengths, different transceivers and vendors that are out there. So there's a lot of issues that could potentially come out of that. But when it starts coming into the protocol end of it, we still see just a certain number of issues where auto negotiation may not have all the different fields being used properly for every situation out there. So yeah.
All right. Well, thank you. And as I mentioned, the slides and a link to the on-demand webinar will be sent out in about a week. And thank you for your time.